Hi, my name is Bloodfish and welcome to my video on the redstone pulse extender. In this video, I'll be talking about what this pulse extender actually is, how to use it, different applications of this circuit, and also different versions of this circuit. Let's get started. As the name suggests, this redstone pulse extender will extend the pulse of whatever has been input into the circuit. So in front of me I have the most basic version of this pulse extender and a stone button. As this stone button has a pulse length of around 10 redstone ticks, and if I press this button, you can see that this button will deactivate before the circuit turns off, meaning the pulse has been extended by the circuit. So how does this work? It's due to the feature of the comparator, which it will output the same signal strength that has been input into the comparator. So if I input a signal strength of 5 into the comparator, after 1 tick of delay, the comparator will output a signal strength of 5 again up to here. This signal strength of 5 will travel 1 block, goes down to 4, travels through another comparator, 4, another block, 3, another comparator, 3, another block, 2, and then so on and so forth until it reaches 0. And now if you add up all the delay the comparator has, it will basically result in the pulse being extended. There are multiple factors that affect the output pulse length of a circuit, the first being the input pulse length. The input pulse length of a pulse extender must equal to the number of comparators in the circuit. So for this case, we have 2 comparators and therefore the minimum input pulse length must be 2, or this circuit will not work. So we have 2 monostable circuits, each will output a pulse length of 1, but because this one is attached to a repeater with a pulse length of 2, this will activate the circuit, just like this. But this side will not, because it has a pulse length of 1. There's another consequence if you have a pulse length lower than the number of comparators, which is shown over here. If you have a pulse length of 2 for a circuit with 4 comparators, you may result in a clock, like this. This is undesirable because it doesn't give a constant output. So it's best if we have a 4-tick pulse and 4 comparators, like this. Which brings me on to my second point, which is the number of comparators per side will also increase your output signal length. So if we compare these two circuits, this one and this one, we can see that this one will stay on for longer because it has more comparators, meaning it has a longer delay. And the final factor that will increase the output signal length will be the input signal strength. Now these two inputs have a different signal strength, which inputs into this comparator, like here. So this input will input a signal strength of 15, while this will input a signal strength of 8. And now this is what this essentially does is it will make the pulse loop the circuit longer. So like this, you can see this stays on for longer compared to this one because it's a lot stronger, basically. This upcoming section of the video will be a bit complex, so if you don't want to listen to this, you can skip to the timestamp indicated for the next section. Anyways, in this section I'll be talking about how different factors, which I've mentioned just now, can affect the output pulse length. So here I've listed out a few of these variables just for reference, and I'll be talking how you can derive the output pulse length by factoring in the effect these factors have on this circuit. So anyways, before we start modeling and deriving, I have a few assumptions to make so we can make this modeling a bit easier to understand. So the first assumption is to assume that the input of the pulse extender is directly next to the input comparator. In the diagram to the right, you can see the input comparator is this one on the right, the one with the triangle pointing upwards, and the input is directly next to the redstone that goes into the input comparator. The reason for this, well, if I put the input over here, then the redstone has to travel another block, meaning the signal strength would decrease by 1 more, which isn't really favorable and makes things a bit more complex. So it's better to put it here. Secondly, we assume the number of comparators equals to the initial pulse length. So in this diagram again, we have 2 comparators and therefore we want an initial pulse length of 2. The reason for this is because we don't want a time delay when the initial pulse turns on to off. So when the pulse travels around the circuit once, after it does that, it should immediately turn off, so the pulse extender will decay immediately. So there's no time delay and it's better, I guess. And finally, we assume the output is opposite of the input, just for consistency. In front of me I have a diagram showing how a pulse extender works. So first of all, you can see I'm showing this frame by frame, so you can see what changes between each frame and also count how many ticks have elapsed after the change, I guess. And secondly, you can see that I've split this into 2 different sections, when the input is on and when the input is off. This is because when the input is off, that's when the pulse extender starts decaying down to 0. So I guess let's start like this process. So in the first tick, let's assume we have a pulse length of 2 and a pulse strength of 7 into the circuit. So the 7 in the input, and the redstone next to it becomes a 6. In the next tick, this comparator will detect that, oh, it's being powered by 7, so it also outputs a 7. And obviously the redstone next to it becomes a 6. In the next tick, this comparator detects the 6 behind it and then outputs a 6. This 6 will decay down to a 5, but because the input is still on, that's why it's still a 7. And then the transition between an on and off state will always be 1 tick because a repeater takes 1 tick to turn from on to off. That's simple, I guess. And then when it's off, that is when the decay starts. And so we just start by looking at what changes in the next tick. So if we look at the first diagram here in the off section, we can see that the left comparator will not change because a 6 will output into a 6 in the next tick, but on the right comparator, the 5 will output a 5 in the next tick. So that's what happens. So it goes down from a 5 to a 5, 5 to 4, and then the next tick, the 4 goes down to a 4, 3, and then so on and so forth. This like loops around the circuit. You can see looping, and then eventually it goes down to 0. And how you can find the output pulse length is by counting the number of ticks elapsed, that like how long this output has stayed on for, basically. So the output, as indicated with a red circle here, a red dot, this stays on, this I guess starts in the second tick. So if you count every tick after the second tick, so let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So therefore we have a pulse length of 9 as an output. After some data collection, I have arrived at some results for the standard 2 pulse length input to comparator pulse extender. As you can see, for the input pulse strength, as it increases, the output pulse length does not increase linearly with it. If I extrapolate this data, you can see that the input pulse strength, if it were maybe 8, 9, and 10, the output pulse strength could be 9, 11, and 11, and it goes up in 2s. The reason for this, I hypothesize, could be because for a pulse to reach the output again, so one loop, it has to travel through 2 comparators, meaning it will go up in 2s. Here we are back in Minecraft to show that the data collected is actually valid in-game. So in front of me I have 3 different pulse extenders, each with a different setting. In the first pulse extender, we have an input signal length of 2, input signal strength of 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5. An input signal strength of 5, and hence we assume the output signal length to be 7, as per the data. So again, here we have reference circuit, 1, 2, 3, 4, 5, 6, 7 with a 7 tick delay. So logically, both redstone lamps should turn off at the same time, just like this. And again. In the second case, we have something similar, but we have a different input signal strength. In this case, we have an input signal strength of 15, 14, 13, 12, 11, 10, 9, 8, 7. So we expect an output signal length of 9. Again here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So both redstone lamps should turn off at the same time, again, just like that. In the third demonstration, we see the effect of doubling the number of comparators. So again, we have the same input signal strength. You can see that this aligns with the last circuit. So if we double the number of comparators, we should also expect that the output signal length to be doubled from 9 to 18. We can see here the reference circuit, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, an 18 tick delay. And so both redstone lamps will turn off at the same time, and showing all of this is true. If you haven't already noticed, here's how you build the most basic pulse extender. For this, you need a 2x3 area and 2 comparators with 4 pieces of redstone dust. Now place these 2 comparators next to each other but facing in opposite directions, and then use the 4 pieces of redstone dust to link these 2 comparators together, just like that. Now for the applications of a pulse extender. For a pulse extender circuit, I want something to activate temporarily or for a longer period of time. In my first example, you can see I want this clock to activate temporarily, so I attach this to a pulse extender. Because I know this pulse extender will eventually deactivate, the clock will deactivate with this pulse extender, just like this. And then when this deactivates, this also deactivates. Another use for this pulse extender will be to extend the pulse, so something activates later. In this block swapper, I want this piston to activate first, but deactivate last. So you can see I extend the pulse, so activates first, but deactivates last, because the pulse is still extended. The same logic goes for piston extenders, where I want this piston, like the one at the very back, to extend or deactivate last. So I use this pulse extender to extend the pulse, so this deactivates last, just like that. And of course, a pulse extender, you want to extend the pulse of something. The most common use would be to extend the pulse of when a piston door is open or not. So you can see when I press this button, the button deactivates before the door closes, just like that. So the pulse has been extended. Finally, we have different versions of the pulse extender. The first one is our personal favorite because it's easy to make. You can see we just have a line of repeaters running into blocks, which will hard power this line of redstone dust. So if you can see here, because the repeaters are in a continuous line, the blocks will continuously power this line of redstone, so the redstone pulse is increased and extended, just like that. Now the second extender is a hopper timer, but instead of a sticky piston for this block, we have a normal piston. You can see that this is on for a considerable amount of time, and yeah, like that, it'll deactivate soon, and you can change the pulse length by adjusting how many items are in this hopper, like that. And then finally, we have some sort of like an adjustment to the original one, but it still extends the pulse. We have a block. Yes, this block, it has to be placed where the input comparator should be running into, like this, but this block can double the output signal length of the circuit. This is because on this side of the circuit, the signal strength does not go down, and therefore the signal strength has to go through two comparators for it to actually go down by 1. So if this comparator outputs a signal strength of 5, this will be 5, outputs 5, and then it can only go 4, like this. So it has to go through two comparators. So you can see this is longer than your normal one. It's also like cheaper, so I don't know why you don't use this. But you can't use two blocks on both sides, because you have to have a side where the signal strength can go down, because if it's like this, it just gets continuously powered and it doesn't work like that. This is the end of my video on the redstone pulse extender. I hope you enjoyed it, learned something, and I'll see you in the next one. Goodbye.